Thanks everyone. Very thankful for Ada inviting me to here to Samsung to present some of our latest research on hardware-centric AutoML design automation for efficient deep learning computing. Since we're focusing on algorithm and hardware co-design, this is a really large design space. Therefore, we want to have design automation to have AI to help improve the efficiency of deep learning computing. So computation plays a very important role in modern deep learning, especially the powerful hardware enable us to train larger scale neural networks, and also the more efficient inference hardware enable us to have a better user experience, for example, have a lower inference latency and also lower power, which will attract more users and generate more data. So this is a virtuous cycle enabled by the efficient hardware and computation. However, there is a challenge for modern deep learning, given the Moore's law is slowing down, but the amount of data that's required to train large-scale neural nets is just increasing. So in the future, how do we balance between the difference between the supply of the computation and also the demand for computation in AI? So I have done some previous research at Stanford with my advisor, Professor Bill Daly, on co-designing efficient deep learning hardware and also software. So we propose a deep compression that can aggressively reduce the number of connections in deep neural nets. For example, by pruning, we can reduce the number of connections in FC layers by about 90%. And the amount of connections in conv layers by about 70 to 80%. And then coupled with trained quantization, we can further compress deep neural nets from 10 to 30 times. Okay? So this means we can have less requirement to fetch the data from the memory, to save the memory bandwidth. However, general purpose hardware are not efficient to support the compressed and sparse neural net. So I built this efficient inference engine which directly walks the sparse matrix and ignore those zeros so that we can save the cycles and save the memory for inference. And later we did a FPGA prototype, the efficient speech recognition engine, also called ESE, which is a giant sparse matrix multiplication unit to accelerate speech recognition tasks in LSTMs. So this is an overview of my previous work on the algorithm and hardware co-design for efficient deep learning. So last summer, I joined MIT as a faculty member, and now I have a couple of wonderful PhD students working with me under the new endeavor on the efficient hardware, AI, and neural nets. So we focus on these like H for high performance, high energy efficiency hardware, A for architectures and accelerators for AI, and N for novel algorithms for neural nets. So we target small models for inference, how to save the memory bandwidth, scalable systems for training, how to save the networking bandwidth and make your training system more scalable, and also specialize the silicon to design specialized hardware for the particular AI tasks. So our mission is to make AI more efficient with any resource, any hardware resource and any engineering resource. So we target low latency, high throughput inference and training, and also low power for both the edge devices and also on the data center devices. Since on the edge, usually the edge devices are constrained by the battery, and also on the data center, the total cost of ownership, the electric bill is a major component of the total cost of ownership. And finally, we want to enable design automation for this cross-stack design betveen algorithm and hardware to enable non-machine learning expert be able to produce those models and also run efficiently on the AI chips. So this is the big picture of my presentation. We have algorithm, we have hardware. So in the first part of my presentation, I will talk about how to adapt the algorithm to be hardware efficient so that the algorithm requires less computation and less hardware resource. Okay? In the second part of my presentation, I will talk about efficient hardware specialized for the algorithm. It's a bottom-up approach where we are building more efficient hardware that can provide more computation given a fixed power budget. And then when we have human in the loop, this is a large design space. So we want to have AI assisted design automation to automatically, efficiently do this design space exploration for this co-design. All right, so I will start with the first section, adapting the algorithm to be hardware efficient. And I will present our recent work on efficient video understanding. Since video understanding is more challenging because it's more computation intensive than image recognition. Video usually requires 3D convolution to model not only the spatial information, but also the temporal relationship. So we present this work on TSM, the temporal shift module for efficient video understanding. So the goal is to build efficient spatial and temporal modeling. So temporal modeling is very important for video understanding tasks. For example, given this video stream, putting something from left to right, you can now tell whether it's from left to right or right to left from just a single frame. But you need to see the entire video sequence. And such temporal modeling and video understanding has a wide range of applications. For example, in advertisement, given a YouTube video, you want to predict what kind of advertisement you want to have. And also video recommendations, say you search some of your interested topic and what kind of content matches such content. And also various other applications like surveillance, like self-driving cars. They're intensive workload using for video understanding, both on embedded devices and also on large-scale data centers. So we want to have an efficient spatial temporal modeling for video understanding. Conventionally, this is done by 3D CNN, where we have those joint spatial and temporal feature learning. However, 3D convolution is more computation intensive even than 2D CNNs. So there are also previous efforts using 2D CNNs to do video understanding, for example, TSM. But it cannot handle the temporal modeling really well, and you see the accuracy of those 2D models is a lot lower than the 3D model. So our task is to achieve 3D CNN's performance at 2D complexity. And let's see how do we achieve that. So the intuition is that convolution is basically consists of shift and multiply and accumulate. The first step of shift can be conducted with very little computation cost. And this has been previously explored in the 2D domain. But in 3D domain, we find it's even more promising to offload the multiply and accumulate only to the 2D convolution and only perform shift in the 3D domain. So this is how we conduct the shift as a new primitive to do temporal modeling. So TSM can shift part of the channels in the temporal dimension, which facilitates the information exchange among neighboring frames. So you want to see the entire video frames rather than just 1 or 2 video frames. So the way we do that is, for example, in this example, we have a temporal dimension in the vertical side, and the channel dimension in the horizontal side, and XY dimension in each small block. And what TSM does is basically we shift part of the channels to the bottom, and shift part of the channels, to the up, so that, for example, in here, the blue part is the second time step. It has both the blue part, the yellow part, and also the green part. So it can see a receptive field in the time dimension of 3 frames, right? If you have one such TSM module. So if you can step multiple such TSM modules, you can see the entire video stream, okay? So that's the key idea behind TSM module. And this is a very computation efficient, since the unshifted parts, you don't have to touch those memory. And those shifted part, you only need to move those pointer without performing any multiplication and add. So it's 0 flops and 0 parameters. You don't have to store any weight. So To put in the bigger picture, our whole architecture to do the video classification task here is given a video stream. We sample several frames, and then we pass it through a 2D convolution. Okay, and so that, for example, we have four frames in this example. We just perform the temporal shift part of them to the bottom, 1/4 of them up, and 2/4 of them, half of them remain unchanged, followed by a bypass layer to connect them. So you can imagine the more we shift, the more information we lose in the 2D dimension, but more temporal exchange we want to have. So we did some ablation study later to find the optimal proportion of channels we need to shift. So the implementation is extremely simple. So with just these 5 or 6 lines of code, we are able to achieve the state-of-the-art result on both the something v1 and something v2 dataset. So the idea is we decide how much to shift, and then we shift part of them to the left, shift part of the channels to the right, and the remaining part gets unshifted. So we tested this result, this method on 2 kinds of video data sets. The first kind is less temporal related, like UCF101 or HMDB or kinetics. As you see from the single frame, for example, on the top, I can see from this single frame the lady is playing hula loop. For example, the first one, you can see this lady is applying eye makeup. So not necessary to look at the whole video stream, but for each frame, you can tell what is he or she doing. The second part is more interesting to us, the more temporal related. For example, moving something from left to right, thumb up, or on the right hand side is expanding something rather than closing something. So we can expect on those more temporal related data sets, the accuracy improvement will be higher. And this is exactly the case we observed. So for these less temporal related data sets, on kinetics, UCF, 101, HMDB, we observed about 3 to 7% top one accuracy improvement over the TSM, the 2D models. And on the right-hand side, on those more temporal-related data set, we observed from 13 to 28% improvement of the accuracy compared with those 2D models on both something v1, something v2, and gesture data set. And currently, we rank top first on the leaderboard of both something v1 and something v2 data set. Not only compared with a 2D data set, but also compared with the 3D data set, we did an extensive study comparison with the peer work, including the TSM, TRN, those 2D methods, and also the ECO family, and also the widely used I3D family and its variants. Our accuracy on the bottom, the test accuracy, 46.1% top one accuracy is the best currently on the leaderboard, showing that this TSM module is not only computation efficient, but also it can model the temporal relationship really well as a very efficient primitive that saves the computation and also improves the accuracy. And also on something v2 dataset, it also have a higher performance, a big improvement over the previous work. So currently this is a dataset, something v2 dataset. The leaderboard, we submitted the result like 3 months ago. Currently still ranking top first. So we need a pointer somehow, so it's better to show it in this way. We are ranking top first, and there's a big gap between the accuracy compared with the later result, like 0.1% difference, while the gap here is about 3%. Although there are many submissions like 7 days ago, 3 days ago, 4 days ago, the TSM is a pretty strong, strong method to do such temporal modeling. And the most amazing stuff is that we can aggressively reduce the computation requirement. So the x-axis is the amount of computation per video, and the y-axis is the accuracy. So TSM consumes about 3 times less computation than the ECO family, and also 6 times less computation than the non-local I3D family but achieving higher performance on this data set. And later we did some ablation study to see what is the best shift method and how many channels should we shift. And we find that actually 1/4 or 1/8 of the channel shifting is the optimum. Since the accuracy, they are neck and neck, but we chose 1/8 because the less we shift, the less memory we need to touch, and memory access is expensive, and this method will be more hardware friendly if we chose just to shift 1/8 of the channels. And on the right-hand side, we compared zero padding with circulant padding, and we find zero padding is actually give better accuracy. And why is that? Because circulant padding, you are moving past the frames to the future, right? It will disrupt the temporal relationship. Therefore, we just chose zero padding. And zero padding is also more hardware friendly because it avoids one memory copy. And finally, we have some demo showing the throughput improvement measured on this Tesla P100 GPU. The left-hand side is the popular i3D framework. It can run at a throughput of 6 videos per second and 41.6% top point accuracy. Well, our TSM module can run the video understanding at 77 videos per second and achieve a better accuracy like 43.6% top point accuracy, and improve the throughput by 12 times. So the throughput usually determines the price of your service. So you can improve the throughput by 12 times. It's highly possible you can greatly cut down the cost of a video understanding service, either running on the cloud or running on the edge devices. And not only throughput, but latency is an important metric, right? So this is comparing the latency with the i3D method and also with the TSM module. Using the same backbone, i3D have a latency of 164 milliseconds per video, but TSM takes only about 20 milliseconds per video. For example, if you're putting this task in advertisement prediction, given a goalkeeper is trying to protect the football shot, and then you can immediately put some advertisement only within a couple of milliseconds to give immediate feedback of what advertisement to recommend to the user. So that's quite helpful on the data center services. So we also built some demonstrations to show the effectiveness of video understanding, like moving something from something, hitting something with something. Those are predicting the actions, predicting the temporal relationships, like covering something with something. This is not doing object recognition, so the object is just something, but it's modeling the action by like hitting something. Or moving something up, moving something down, etc. And we can also use single-sided TSM to do those online video understanding. So, previously, we move in both directions, right? Move down, move up. Now we only move past frames into the future so that we can do online video understanding. This is a real-time demo.
This is a hand.
For hand gesture recognition, there's a video link on the bottom for remote viewers. So we are basically running the video understanding on this Jetson TX2 board from NVIDIA mobile GPU, and you see the fan is not running. It's only taking about 7 watts of power. And we have both the camera view and also the screen view. And you see on the right-hand side is doing the prediction of the gesture right here, like swiping up, swiping down, or moving left, moving right, or zoom in the map, zoom out the map, and can run at about 15 frames per second, which is quite high considering we are using such a low power device. And this can be used in, for example, in TV products to have a better user experience interacting with the TVs, right? And also in smart vehicles where you can control your car without having to touch the car. All right, so the take home from this project where we can do both acceleration and also improve the performance, I take the, this is the word I really like from Bill Daly in the ISCC 19 panel session on how can hardware designers reclaim the spotlight. Bill mentioned the boundary between the hardware and software is blurred, right? So we are using a software approach to do the acceleration. So often need restructuring the algorithm to utilize the memory efficiently, right? So in this TSM work, we are just restructuring to find a new software primitive to do the temporal modeling that has less access to the memory, and we don't need any weight. It's 0 parameter. You don't need actually to store those weight at all that can utilize the memory efficiently and reduce the memory bandwidth. And another take home is the Occam's razor. Occam's razor says one should not increase beyond what is necessary the number of entities required to explain anything, right? It's also known as the law of parsimony, right? It's the problem solving principle that states simpler solutions are likely to be correct than complex ones, right? So the shift is a simple primitive than convolution, but still it performed both better in accuracy and better in the latency and throughput. So this is a rule of thumb in my research for software and algorithm and hardware co-design. All right, so having talked about efficient algorithms, let's talk about this bottom-up approach to design efficient hardware primitives specialized for the algorithm. So I will talk about recent work on the efficient intersection and union engine to accelerate the sparse applications, the sparse workloads. So why intersection and union is important? So intersection and union are basic operations for sparse linear algebra. For example, sparse element-wise multiplication is finding the intersection of the non-zeros. And sparse element-wise add is finding the union of the non-zero element. And sparse linear algebra is widely used in sparse neural networks. For example, after pruning, the weight is sparse. And after redo, the activation is sparse. And we have seen the sparse engine from Samsung back in Tuesday, which is amazing work accelerating sparse neural networks. For example, we are having the sparse format with both the index and value. For array A, you have index of 1, 4, 7, and value of A1, A4, A7, and array B with index of 3, 4, 5, 7. Those are non-zero entries. We're only storing those non-zero entries. And element-wise multiplication result would be, the index will be 4 and 7, and the result will be A4 times B4 and A7 times B7. But if you fetch all the data, all the entries from the memory, like A1 is actually not necessary because B1 is 0. So you don't need to fetch A1 since the intersection is nothing. This will save the memory bandwidth if you don't need to, if you can find the intersection of index early before you load the data, right? For example, A1, you doesn't have to load, B3, you doesn't have to load, B5, you doesn't have to load. This way we can save the memory bandwidth. If you have such a unit sitting close to your memory or sitting close to a disk to help filter out a lot of redundant data movement. So the software implementation is not efficient. So for example, finding the intersection of these two arrays, you need to maintain 2 pointers. And each time you need to move the pointer to compare, okay, 3, we find an equal, then we have an output, then we move the pointer, move the pointer sequentially, give another output, move the pointer, finish. Okay, so this process is sequential and it takes O(n) complexity. So we want to accelerate it by parallelizing the comparison. The basic operation is comparison. So we want to parallelize the comparison in space rather than serializing them in time. Therefore, we propose this array of comparators where we have one array on the left and one array on the top. And every time we are just doing the comparison of the left entry and the top entry to see what is the relationship between the left entry and the top entry. And we find the boundary of this comparator array will give you the output of the intermediate results. And then we can reset those repetitive items to get the union result. and find those repetitive items to find the intersection result. And all the operations can be just done within one cycle without having to run those complicated instructions. And we can further hierarchically scale up the array to have this hierarchical processing to handle longer arrays. We can handle an array of array by having the last element of each subarray in the first hierarchy and the remaining part to be the second hierarchy. Since if the largest element of one array is smaller than the smallest element, then the intersection would of course be 0. So in this way, we can eliminate lots of redundant computation. All right, so we did the prototype of this architecture on the Xilinx FPGA, and we compared the throughput running on the CPU on the same SoC. The CPU takes about a quarter watt, and the throughput is about 86 million ops per second. And all the data is pretty long, so it's an apple-to-apple comparison where we are putting all the data on DRAM. So the FPGA is also using this scenario, is also putting all the data in DRAM, but it can achieve 30 times more throughput on union and 32 times more throughput on intersection. And if we increase the array size to 16 by 16 array, the intersection actually can have 51 times better throughput because previously it was computation bounded. Now increasing this array size will make it have more relaxed this computation bound. Well, the union operation, since the output is more, it takes more memory bandwidth. It's memory bounded, so increasing the array size doesn't improve the throughput. So we also talk about hierarchical array, right? So on the fourth line, we have a hierarchical array of 4 and 4 to have an array size of 16. You see, it consumes less dynamic power than the 16 by 16 version, which is more efficient, but still the throughput is similar, 30 times on union, 51 times on intersection. And we can also using a lower bit width to further improve the efficiency if the size of our array is not that large, but still both scenarios we have an order of magnitude improvement of the throughput, even if we scale them into the same power to have an order of magnitude better energy efficiency. So we also compared application using such primitive, which is triangle counting, which is widely used in analyzing the social graphs. Comparing the CPU and FPGA and the GPU, the EIUE is about 46 times better energy efficiency compared with the CPU baseline. This is the demo of the unit running on the ZCO102 development board from Xilinx, which is a hybrid board, SoC having both ARM CPU, which is the result on the top, and also the FPGA, which is the result on the bottom. We see the FPGA takes very instantly, like 157 milliseconds to process, while the CPU is taking a long time to finish the processing. 4K million ops versus 76 milliseconds. So it's a very helpful, very small engine that can help filter out potentially lots of the redundant memory access if you can have such a small engine sitting in your say DRAM controller or SSD controller. So that's some of the future work we are interested to do. All right, so we finished the second chapter, which is building efficient hardware to provide more computation. Now, when we have human in the loop to do the cross-stack design, the space becomes pretty large. So we want to have those AI-assisted design automation that can help our engineers to do the design space exploration. And we'll see how AI can help design those AI chip and also the neural networks. So the goal is, previously we need machine learning expert and also hardware expert to do this design. Like when I was doing the startup, I find it's quite difficult to hire engineers that master both machine learning and also hardware. Therefore, we want to democratize this thing and enable non-experts by taking advantage of this called hardware-centric AutoML, so we can push the button and automatically design you the neural network and also the chip. So I will present our recent work on Proxyless-NAS direct neural architecture search on the target task and target hardware as our initial endeavor for such AI-assisted AI or design automation for AI software and hardware co-design. So our goal is to have a CNN design that's specialized for your hardware, right? So TPUs, GPUs, IPGAs, mobile SoCs, different chips may have completely different preference on the optimal software, on the optimal neural network. For example, Samsung recently have the customized chip presented as SCC, right? So what is the optimal neural network that's catering, that's exactly fitting your chip for your AI chip? Rather than having ResNet or Inception running across all chips, we want to have specialization, right? Specialize your neural net model for your hardware, right? So from single core, multi-core, now we are in the area of specialized hardware, but this is another direction where we are having specialized software. Since the design cycle of hardware is pretty long, so we want to take advantage of, we are able to specialize the software. However, conventionally, the previous NAS is very computation intensive, making such specialization very challenging. For example, the initial NASnet took 48,000 GPU hours to process. So that equals to 5 years on a single GPU, and the darts would have taken 100 gigabytes of GPU memory if it searched directly on ImageNet. So this is very prohibitive to specialize. And another drawback is previous work has to rely on the proxy task, like learn from CIFAR and then transfer to ImageNet. A model work on CIFAR may not work very well on ImageNet since they have completely different model capacity. And also we want the previous work search from small architecture space and then transfer to large architecture space, for example, repeating the building blocks. And we find actually the input module and then also the deeper you get, the architectures, the modules are quite different, or using fewer epochs of training and transfer to full training. So our goal is to enable proxyless neural architecture search for your target task and target hardware, so we can specialize the model for the hardware. And we want to reduce the GPU hours and GPU memory to the same level of normal training, and also cooperating the hardware feedback into the search space. The method we adopted is combining the efforts previously I worked on model compression to neural architecture search, where we can use path level pruning to reduce the GPU hours and also the path level binarization to save the GPU memory. So this is the implementation where we have all the redundant paths in our design space. We have those weight parameters illustrated in green, and also those architecture parameters shown in yellow. So we learn both the weight and also the architecture. And in the architecture parameters, alpha, beta, so we binarize those parameters to enable only one path to reside in GPU memory at one time. So even we have a large design space, the memory constant is, the memory required for such search is constant on the GPU. And also we did a latency model to take the direct feedback from your hardware, right? We want to specialize the model for your hardware, so we need some feedback from hardware. But directly measuring the hardware performance may suffer from variance, like thermal throttling, and you need lots of hardware devices. So we built a latency model to predict, given the model, predict the latency, and the latency can be quite accurate. On the right-hand side, it's very close to y equals to x. So the x-axis is the estimated latency, the y is the real latency. And another good thing is with the model, we can make the latency also differentiable. So we can do back propagation, including the reward function from the latency. All right, so given above efforts, this is the result on ImageNet. We are able to achieve 1.8 times faster inference speed measured on this Pixel 1 mobile phone. Compared with the current industry standard, the MobileNet version 2, with very similar accuracy, we can have about 1.83 times lower latency. So mobile platform. And comparing previous result, which is including both the manually designed models and previously neural architecture search. And you see previously neural architecture search took like tens of thousands of GPU hours. All these results are done by Google. because Google has a very amazing amount of computation resource. But in our research lab, we don't have much computation resource. But still, we can do the search with only 200 GPU hours, like 200 times less GPU hours. But we can do better. We can have a higher accuracy, like using the same setup. We achieved 74.6 top-point accuracy with a similar latency measured on the Pixel 1 mobile phone. And this is the floating point results. And also, we can search a specialized model for the GPU platform. And we can achieve like 20% better latency, 1% better accuracy, given 200 times less GPU hours. And we can also search the model specialized for your CPU. So this is comparing MobileNet, MNAS, and ResNet. So compared with ResNet 34, we are about 2% higher accuracy, and the latency reduced from 58 milliseconds to 38 milliseconds. So no matter if you are a data center workload or mobile workload, you just need to change the underneath latency model, but the search code base can remain exactly the same. So that's the beauty of this work, where we can have a low efforts, but to specialize the model for your hardware. An interesting phenomenon we find is the specialization is really needed, since a model good for one hardware platform does not run fast for another. So we find that diagonal latency is the lowest. So GPU model worked best on GPU, CPU model worked best on CPU. And this is the search history visualization of different hardware. On the mobile, it's on the top, CPU in the middle, and GPU on the bottom. Previously, people have almost forgotten about the 3x3 layers, and the AI agent learned something that human engineers almost doesn't believe in before. For example, the red layers are 7x7. And neural network architecture designers seldom use 7x7 layers. But the AI agent find actually in the later layers, 7x7 layers are actually quite helpful. Extensively use the 7x7 as opposed to our wrong heuristic where 7x7 is not useful. Because 7x7 compared with 3x3 kernels, they have two less kernel calls and less feature maps. Therefore, the search really makes sense. And also, we find the GPU model is shallower than the CPU model because GPU has more parallelism. GPU also preferred the large kernels and fat and wide kernels because it has more parallelism. So there are quite some insights during this neural architecture search with Proxyless-NAS. And this is the final model, in case the remote audience cannot see the video. And we opened the Proxyless-NAS model on GitHub with both the CPU model, the GPU model, and the mobile phone model. And if Samsung have come up with a new phone, we are very happy to see what is the best neural network architecture for the new AI chip. And I will then briefly introduce our recent work on hardware-aware automated quantization. Again, it's in the big picture of design automation assisted by AI. So multi-precision chips are a big trend. For example, in A12, there's a small line here saying multi-precision support. NVIDIA GPU also support multiple precisions, ranging from P32, P16, int8, int4, and int1. So how do we decide the precision? So for multiple layers, for both weight and activations, this is a huge design space, like 8 choices for weight, 8 choices for activation. That's a total of 64 choices. And if you have n layers, that's 64 to the n choices. Again, we want to use an AI agent, reinforcement learning agent, to do the design space exploration, rather than using humans. And in order to provide feedback, we plugged in a hardware simulator to provide a direct feedback from the hardware. And we used different kinds of simulators to show that on the edge and the cloud, the preference is quite different. So this is the result of Pareto optimal curve compared with the fixed 8-bit quantization. The flexible bit quantization can lie on a better Pareto optimal curve on this trade-off between latency and accuracy. So this is the process of the search. So the RL agent first preserves the accuracy, and then it reduces the latency and energy, and then and finally the reward get stabled. So this is a multi-objective optimization problem where we are optimizing both the latency, the energy, and accuracy. So by plugging the hardware simulator, we can collect those hardware counters and also efficiently model the energy. And we want to interpret the quantization policy on the edge, right, to see whether the policy given by the automated AI agent makes sense. And we find depth-wise layer gets allocated with fewer bits, and point-wise gets allocated more bits. And why is that? We studied a roofline model to see the operations per byte for both the point-wise layer and also the depth-wise layer. Point-wise is more computation reuse, and depth-wise layer has very little computation reuse. Therefore, it's memory bounded. On edge device, there's very small memory bandwidth using the DDR3 memory model. So they get allocated with fewer bits to reduce this bottleneck. And on the cloud, we observe the contrary, where depth-wise more bits, point-wise less bits. This is because on cloud, we allocated more memory bandwidth in the simulator, which is HBM. Therefore, those computation-bounded layers, like point-wise layers, they get allocated with fewer bits. So an AI agent wasn't exposure to such roofline model, but it automatically discovered this phenomenon, which is quite amazing. So the take-home is we want to have hardware-aware automation and specialize the decision for different hardware. So we have another piece of work on defensive quantization, which I may not have time to describe today, but basically the idea is model compression and quantization is not free lunch. We want to balance between the efficiency and also the security of the model. Conventional quantization method will actually hurt the accuracy. There's a big gap when under adversarial attacks. And to cope with that problem, we designed this Lipschitz constant regularization to regularize the Lipschitz constant. And as a result, we can actually turn quantization into a helper against adversarial attacks rather than conventional vanilla quantization will hurt the adversarial attack robustness. And the take home is we want to raise people's awareness about the security of the quantized and deployed neural networks to balance between efficiency and robustness. And we designed a novel defensive quantization to defend those adversarial attacks while still maintaining the accuracy. And for more information about this work, you may reference my website for the iClear 19 paper. All right, since time is limited, I will wrap up the presentation today. We want to have design automation for neural networks. Compared with previously the three big components of deep learning, when we have the big data, computation, and engineers, we want to enable design automation to have machine intelligence, not to replace human engineers. We still need a lot of human experience, but to assist and help humans to make different kinds of decisions, especially given the large design space with algorithm and hardware co-design. How do we design the models? How do we design the AI chip? And how do we systematically design them all together to provide the best energy efficiency? And this will require more computation in the future, right? So designing efficient training hardware will also be quite helpful. We have some recent work on large-scale distributed training as well. You may reference my website, but may not have time to describe in detail today. So to wrap up, today we talk about three sections. The first section, we talk about how to build efficient algorithm that's hardware friendly. We talk about the TSM module for efficient video understanding that improved the throughput by 13 times and also is the state-of-the-art accuracy on those leaderboards. And then we talk about the efficient hardware that provide more computation for the algorithm. For example, the efficient intersection and unit that can potentially sit in close to the memory to help you filter out a lot of the redundant memory access for those sparse linear algebra or sparse workload. And finally, with human in the loop, we talk about design automation that saves human resource. We talk about the focus on the Proxyless-NAS, right? Specialize the model for your hardware, for your AI chip, right? an HAQ, specialized quantization policy for your AI chip. And in the future, I believe this is just the area is just beginning with such efforts on design automation and hardware-centric AutoML. There are lots of low-hanging fruits that still needs to be collected. And with the excitement of the amazing work from the Samsung, the specialized accelerators on the phones, on different devices, on TVs, and also on the data centers, I believe there are lots of opportunity to collaborate in the future to explore this large design space together. And very glad to come here, and thank you so much for having me here, and thank you for your attention. I'm glad to take questions.
Basically, I have two questions. The first one is, how's the difference of your work compared to the work, let's say, TVM, developed in University of Washington?
Yeah, the question is, how is the work different from TVM? So there are different layers of the optimization, right? The model design layer, right? And the model framework, right? And also the underneath hardware, right? TVM is the framework part for the kernels, for the scheduling policy, right? But Proxyless-NAS is on the upper side of this of the stack, right? We design models, and also we design hardware. So different stacks.
Okay. My second question is that in your you mentioned the AI automated chip design, right? For that part, so the design automation part, you mentioned the AI agent is using a reinforcement learning algorithm, right? So my question is, how is that, in terms of sample efficiency, how's that compared to more traditional optimization algorithm like Bayesian optimization?
Yeah, that's a good point. Actually, I have some slides for that. I didn't have time to present. This is the sample efficiency we compared with the human expert and random Bayesian optimization. You see, Bayesian optimization using the same time can only explore 800 samples, right, while we can explore 50,000 samples. And Bayesian optimization even doesn't meet the spec of the circuit design. And also, this is another example where our reinforcement learning agent can meet all the circuit design specs, bandwidth and gain, while under the same time limit, the same search time, Bayesian optimization cannot meet the design spec.
Okay, but what's the reason you only sample 1,160 compared to the reinforcement learning algorithm?
Because Bayesian optimization grows cubically, the sample, the search time.
I see.
Right.
But provided that you have a better, Bayesian optimization model, which you do not take into account that part, then what's the sample efficiency compared to reinforcement learning algorithm? So that's my question.
This is in the same constraint of the end-to-end clock time you do the search, right? Given the same search, what's the best result you can get? Bayesian optimization give a bandwidth of only 72 megahertz, while our DDPG agent give about 92 megahertz.
Right. I understand. For Bayesian optimization, you are talking about the cost of the model itself, right? Because when you have more samples, the time to train the Bayesian optimization is going cubic. But what I'm saying is that if you don't think about that cost, let's say
you need to think about the cost. You have limited hardware resource and time to search the policy, right?
Right. Okay. Thank you for your question. Thank you for answering.
Yeah.